All right. Good morning, wonderful people. All right, let's go ahead and move over to what we're doing today. So I got our objectives here. So what we're going to do today is we're going to classify real numbers and identify the application of real numbers. And lastly, apply the properties of real numbers to evaluate an expression. So what are natural numbers? So natural numbers, kind of a review. Natural numbers are numbers that kind of occur in nature. So, think about the number of rocks or the number of sticks. You can have 1 rock, 2 rocks, 3, 4, 5, or 6 rocks, whatever, and so on. You can have that many rocks, basically. But if you tried to explain to a squirrel, 0 rocks or 0 acorns, they probably wouldn't really understand what you were saying, because they don't really see 0 as a number. They don't have that level of comprehension to say, wait a minute, 0 is not a number. Or wait, no, they would say 0 is not a number, but they would say that, 0 is nothing, so why bother saying it?
Yeah.
And then we have whole numbers. So what are whole numbers? So whole numbers, well, are basically the same things, but they do include 0. So we have 0, 1, 2, 3, 4, 5, and 6, and so on. So that's what those 3 dots means. The 3 dots means that it goes on like that pretty much forever. So, to infinity, whatever you have, I'm pretty sure there's a lot of rocks around. But that's just a quick recap of what the 2 basic types of numbers are: natural numbers and whole numbers. So the next set is integers. So with integers, this is kind of it's kind of an extension, because we're looking at our positive numbers, which would be pretty much our real numbers. So 1, 2, 3, 4, 5, 6, on up to 10. And this thing here means it goes on and on forever this way. So you are going to get a lot of numbers that go that way. And then you have your 0, which is not positive and is not a natural number, but 0 is included. So we have our integers. And then as we go left, or as I like to call it sometimes, backwards or back, these are our negative numbers. So each number has a negative value as well. So you can think of it like a number. Every number has their opposites. So that's what we call them. We call them their opposites. So like if I wanted the opposite of 5, the opposite would be -5, because it's the same distance, but just in the opposite direction. So there you go. We got our positive, our negatives, and 0. So 0 is kind of a weird number because it's not positive or negative, but it is what we call neutral. It's neither of those things. And there is only one 0, and it is not -0. So there's no such thing as -0. 0 is just the middle of them, right? So you can think of it as where you go from negative to positive numbers. So those are the 3 types of integers. So again, integers includes whole numbers, real number, natural numbers, and 0. So it includes all of these 3 things here. So by this time, hopefully you're pretty good at working with integers. Go ahead and explain a little bit about where you can see some of these numbers happen in real life. So where you can find real world integers, coldest temperature. So this is one that I remember a story about this one here. So I know I had one student when I was mentioning this -4 degrees. I once had a student who was like, well, wouldn't you just like die or something? No. Your freezer naturally goes below freezing all the time, and you can walk into a freezer at Burger King or restaurants, and they have these big freezers, and you can go in there and you can spend several minutes in there and not die. So I'm not really, but yeah, it will freeze. So that's usually called below freezing. So 0 degrees would be like almost freezing, and anything below 0 degrees. So if it's colder than 0 degrees, that's a negative temperature. Although some of these are still positive. So 10 degrees is still very cold, but not really like, again, freezing to the point of where like it would be pretty cold, but you wouldn't, ice wouldn't freeze into that. So let me go to the next one. So this next one here, I don't really see a lot of game shows anymore, and I don't know if kids these days would understand the game show idea, but back before reality television was a huge thing, you would basically have these contestants play a game, and they would answer questions, and they would get points. And if you got one wrong, you would lose that many points. So in this case here, we have two contestants that have negative scores. And I don't know what the exact rules are behind that. I don't know if they have to like pay that money back or anything like that. But it was possible to get a negative score in that game. Looking at some other ones here, we have altitude. So if you imagine like the ground or the earth, right, you have some areas that are really low. And then you have some areas that are above the water line. So the earth is covered in water. So if we have an ocean here, that's usually what you consider to be sea level, which would be 0 degrees. I mean, sorry, not 0 degrees. I'm still thinking about the last one. 0 feet above sea level. So like a mountain would be above sea level. So if you've ever gone to like Flagstaff or something, or any other town for that matter, where you're on a road, you'll see these signs that say altitude, and it'll tell you what the how high above sea level you are. And some areas can actually be below sea level. So like in this case here, we have Death Valley, which is really low. So it's actually below where the ocean would be, which is about 227 feet below sea level. That's why it's so hot there. So like you notice certain places like Phoenix, when you go downhill, it gets hotter. That's just the way it works. And you may also have seen videos of rocket launches, and they always count down. So they'll usually start off with T- and then count it down. Although again, I'm not really sure how often people see those anymore. But back when I was a kid, the rocket launches used to be like the thing to go do, and you would like watch it on TV or something. The next type of number, so we covered natural numbers, whole numbers, integers. So now we're moving on to the fourth category of numbers, and this is rational numbers. So numbers on the number line, okay, and its opposite, again, those are positives and negatives. But we're going to use these exact numbers to create another series of numbers. So take any two numbers from that number line, all right? So like I can take 2 and divide it by 3. Now, if I took 2, which I'm going to mark right here, and I divided it by 3, so I have 1, 2, 3 equal segments, you'll notice that one of these does not match the line. So it's actually about less than 1. If you were to grab a calculator and you were to take that type of number, so here I have 2 divided by, I accidentally pushed another button. So 2 divided by 3, you would get a number like this, 0.666666. So that's not a whole number. It's not a natural number, and it wouldn't be an integer. So you can think of these like fraction numbers or decimal numbers, numbers in between other numbers. So again, 0.6666, repeat, is between 1 and 0. You can also have the negative version of that number too, so negative 2/3, and it would still be a rational number. So what is a rational number? So a rational number is something that can be written as a fraction. So basically, if you can turn it into a fraction, it is a rational number. But you might be looking at this number 4 and wondering, wait a minute, why is the number 4 a rational number? It's not a fraction. But remember, the definition is a number that can be written as a fraction. So if I want to make 4 into a fraction, I can divide it by 1. 4 divided by 1 is still 4. And I could show you on the calculator, but you know, you can easily easily figure that one out. Oops. But like in this case here, I have 7 divided by 1. It is a fraction, but actually it would just be 7. So you can think of it like if you have 7 Skittles and you are only sharing it with yourself, then you get all 7 Skittles. You could also divide 0, but you're not going to get anything other than 0. But this also includes numbers like this 2.4, which is the result of dividing. Actually, you know what? Let me go ahead and show you on here. So let's go ahead and look at 2.4. So 2.4, and it can be different in many cases, but if I have something like this, so 24 divided by 10, all right, I'm just picking 2 numbers and I can divide them to get 2.4. So it can be written as a fraction of 24 over 10. So it can be written as a fraction. So even though this is not a fraction, it can be written as a fraction. And the same is true with 0.17, or negative 17 hundredths is the way we would say that number. That would be a negative decimal. Negative, let me just go ahead and write it as a fraction. It would look something like that. Negative 17 over 100. So again, it can be written as a fraction. Now there is one thing, and it says that the bottom number cannot be 0. And if you've ever tried that, it's not going to work out. So you get something, I would encourage you to try it out on a calculator, but it is something, and it's different, but what we would call that undefined. And again, a lot of calculators are different. Some will say error, some will say, I've tried it with several different calculators, and I usually have students try it, and it always comes out to be something different almost every time. Let's go ahead and look at some of these really quick. Now, for this lesson, you probably won't need too much of this, but let's go ahead and take some of these fractions and look them over and see what we get. So 5 divided by 8. And we get a nice little fraction that does, that sort of stops. It stops after 3 numbers, so 0.625. This is what we call a terminating decimal. Terminating simply means ending. So this number ends. But there are some numbers that do not terminate. Like for instance, the second example, 7 over 11. So in that case, 7 divided by 11, we get a number that, well, we call this a repeating number, because if you look at the pattern, it goes 0.636363636363. But it does not terminate. In fact, this keeps going on and on forever. Now this calculator can only show so many numbers, and it can't show all the numbers, so it rounded off this last number. But those are the 2 things that numbers can do, the rational numbers, that's what they can do. They either repeat or terminate. Sometimes they even do both. Okay, irrational numbers. So what exactly is an irrational number? And again, I'm going to go back to the calculator for this one here. So let's go ahead and look at that first example of what it gives us. So I'm going to go ahead and switch over to the calculator. Just remember these examples. We have the square root of 3. So 3 and square root. So there we go, square root of 3, and we get this 1.732050875. And it keeps going, but you notice that we don't have any numbers that repeat themselves. This number does not repeat itself. It just, in fact, it's kind of unpredictable. Well, I mean, you can predict it, but to most people looking at this, they would say I don't know what the next number is going to be because it doesn't repeat itself. So this is what we call an irrational number. So sort of like irrational people, they go on and on and on and don't make any sense. And the same is true with the other one too. The other example it gives us is the square root of 11, and you get the same thing. Now I'm going to skip ahead to the last one, and we get the square root of 16. So I'm going to go ahead and take 16 and take the square root of it, and we get 4. So this is not a number that is weird. It's a 4 is a fairly normal number. So if we asked for the square root of 16, it would be pretty easy for someone to say 4. Now, what exactly does that mean? So the square root means the number that we need to multiply it together. So 4 times 4 makes 16. So what are the two numbers that we multiply to get 16? Now, if we try to do this, and I said, think of two numbers that are actually the same number to multiply to get 3. Well, there really is no number I can multiply the same number to get 3. So if I try to, let's try that really quick. So 3 and square root, and we get this 1.732 number. So let's clear this up. So if I say 1.7 times 1.7, we get a number very close to 3, but it's not exactly 3. And the more numbers I add, the closer and closer we get. So 2.95 is even closer than the one we had before. And the more numbers I add, the closer and closer we will get to 3. And we might get something like 2.9999, but actually it's really going to be difficult to get 3. So these two numbers are very, very close to 3, but we just can't get to 3 exactly using the numbers we have. And again, the numbers have to be the same. We can't use something like 1 times 3. It has to be the same number. So to wrap it up, irrational numbers versus rational numbers. So this is actually where we get into the packet. So if you look at the packet, that's what it says here. So rational numbers can be in decimal form, and they either terminate or repeat. Rational numbers can always be written as a fraction of a over b, where a and b are integers. So basically that just means that it has to basically be a whole number, whether it's positive or negative. You cannot have something like, just an example. So you can't really have something like this. Now, you can get an actual value out of that. You could make it into a number, but that's just not the way fractions are normally written. It's just, again, not very typical of fractions to be written like that. So you'd probably have to change it a little bit. So to make it something, and I'm going to go, since I already brought this up, I'm going to have to turn it into a decimal so that there are no decimals inside of the fractions. All right, so irrational numbers are numbers in which the decimal form never terminates and does not repeat. So like in the calculator that we just saw, it's the one that keeps going on and on and on and does not repeat itself. So some examples of that are pi. So that's like the 3.14 number that you usually use when working with circles, and the roots of non-perfect square numbers. So 4 and 16 are perfect square numbers. If you take the square root of them, you will get a whole number. But if you take something like 9 is a square number also, but if you take something like 8, 7, or 6, and you take the square root of those, you will get irrational numbers. So here's a diagram that they give you on what it looks like. So these are the codes that they use for natural, whole, integer, rational, irrational, and real numbers. So on the packet that you have, let me see if I can show you. It's going to look something like this here. So you can go ahead and fill this in. And I left the code on top here, so if you're following along, you can go ahead and fill in your packet. So irrational is I, and some of these are a little bit confusing, so be careful of that because integers are Z, even though both of them start with I. Rational numbers are also going to be Q because actually R means real number. So since R is real number, rational has been assigned Q. Which all of these are rational numbers. And integers have been given, wait, oh, I already said that part. But whole numbers and natural numbers, those ones make sense because whole starts with W and natural starts with N. And here are some examples that you can kind of see as we go filling this out. So pi is the example, and I don't think I have pi on my hand calculator here, but let's go ahead and move over to another one. So if I take 72 and I take the square root of 72, see if I can show that. Push the square root button. We get this 8.482, or was that 52813. So that is a irrational number because it does not repeat or terminate. The same would be true with 41. So again, as long as it's not a square number or what we call perfect square number. So perfect square numbers are numbers that you multiply two of the same numbers to get, like 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 5 times 5 is 25. So 25 in that case would be a square number. Rational numbers. So again, these are some examples of rational numbers, numbers that can be written as decimals or fractions. And that doesn't mean they have to be written as decimals or fractions, because if a number is rational, so here's the Q, if a number is rational, it could also be one of these inside numbers. So like, for instance, let's look at a whole number. I have a better diagram on the last slide for this, but number groups, if they are inside of another circle, they can also belong to that group as well. So again, a whole number, like for instance, let's go with 90. This is a pretty easy one to go with. So 90 is an integer. It is also a rational number because we can write it as a fraction of 90 over 1 or 90.0. And well, in this case, it can't really be an irrational number because if you look at the diagram, irrational numbers are on their own little circle outside the rest of the diagram. So be careful. Some of these are not always, they don't always go exactly together. So I'm going to go back to that diagram really quick and just sort of show some more examples of this. I'll come back to this in just a second. So in this case here, so again, if you have a whole number, like in this case, it gives us 0. 0 is also an integer, and it is also a rational number, and it is also a real number. But if we have a number like -3, that would be an integer, but it is not a whole number, and it does not have to be a natural number. So it doesn't have to be it doesn't have to go down into the deeper circles, but it will be right here. So again, -3 is integer, but it is also rational. Whew, I don't know if that makes, I don't know how much sense that makes, but that's the way it is. So I'll give you a minute or two to copy this if you need to. All right, so let's go ahead and put these numbers into the sets to which they belong. So for instance, here I have, well, -10. So what number does negative 10 belong to? So we got to think of the most specific example first. So in this case, it would be an integer. So let's go ahead and put I, because it's an integer. And if we look at our chart, so I got my chart right here. Oh, and sorry, integers are, I think I made a mistake on this thing here, because integers should be Z. So actually, again, it's a bit confusing, but yeah, Z would be the, for integers. And then the next one, okay, so it's an integer and it is also rational and it is a real number. Oops, real number is E. That one wasn't a mistake. I just pushed the wrong button. So it is an integer, it is rational, and it is a real number. So there we go, that's it. We got all of that sorted out. Let's go ahead and look at negative 30. Now be careful with some of these because we should try to work it out. So if I got my calculator here and I were to punch in 30, so 3, 0, and square root, so square root of 30. Well, it looks like we have an irrational number. We got this number here, 5.477225. And it looks like it's repeating, but it's not. Okay, so when it talks about repeating, we have to have a whole set and that exact combination of numbers repeat again. So in this case, it is I, which is supposed to be irrational, which, wow, that's weird. Now, the reason why this is because it really depends on the textbook. And older textbooks actually have different letters to classify these groups. So I'm using a new book. I don't know when they changed it, but it's confusing even for teachers because again, I've seen this change several times myself. So again, it is an irrational number and it is also a real number, which actually most of these will be real numbers. All right, so let's look at 1 7/9. So in this case here, it's definitely going to be a real number, but what else is it? Well, it's written as a fraction, but actually in this case, it is written as a mixed number. So a mixed number is a kind of fraction because you can see that there is a whole number and a fraction. So in this case, that would be rational. All right, so let's go ahead and move on to number 4. So this is 24/8. Now, with some of these, you do have to do a little bit of work because if we take 24 and divide it by 8, we would get 3. So the actual number we're looking at is 3. So be careful, don't be fooled by some of these because if we didn't do the work, we might say that this was well, it actually is rational because it can be written as a fraction. 24/8 is written as a fraction. So in this case here, it is a real number. So that's kind of a freebie. It's pretty easy to see that. It is also a rational. Make sure I got the code right. It is going to be an integer. It is going to be a whole number and a natural number. So I'm going to just put a little comma in there so we can space out what number it is, what number type it is. All right, number 5, we have 2.48. Now again, if it's a decimal, it's probably going to be rational. And you can look at your chart diagram, which I have right in front of me. And we can see that if it is rational, it might be one of these other ones. So if it's rational, well, it probably won't be any of the other ones. It will not be a natural number. It will not be a whole number. It will not be an integer because an integer does not include decimals or fractions. So in this case, it looks like we're stuck with just rational and real. Okay. Now for this one here, we have to take the square root of 81. Now think about it. Are there two numbers that you can multiply to get 81 and they are the same number? So two numbers you can multiply together to get 81. And you might be thinking 9 times 9. There you go. You got it. It is. Yeah. Okay. I saw it in the chat. Yeah, you did. You put 9 in there, but you know, I probably just needed a second or two to type it. So actually, in this case, the actual number we're looking at is -9. So if it helps, we can put -9 here. So what numbers can we write it as? So it is a real number. And again, I'm looking at my chart here. So it is well, we know it's a real number, but 9 is, it is an integer. So 9 is an integer. So let's go and put integers in there. So that would be Z, and I'm looking at the code. And it is also rational. So let's go ahead and put Q in there. And we're done with that one. Let's move on to number 7. So I have pi minus pi, and I don't have a calculator that's really that good at figuring that out. But if we use our number properties, so number properties are like how they behave. We know that any number subtracted by the same number is going to be 0. So in fact, in this case here, the real value we are looking at is 0. And we know that 0 is, it's an integer. Actually, it's a whole number as well. So it is a whole number. It is an integer. And looking at our diagram, so it's a whole integer, and it's also a rational number. And it is a real number. So again, start from the inside number. So in this case here, it's whole. And that means that it will belong to everything that, so whole number is inside of rational and integers. So it'll belong to both of those, and they all are real numbers. Whew. Okay. So what about this one? What is 16 over 25, and both of them are the square root? Now this one's a little bit of a tricky one. So in this case, it would be, if we take the square root of 4 and the square root of 5, we would get this type of fraction. So I used the square root first. So again, square root of 16 and square root of 25. So this is just sort of a shortcut we need to do. This is actually something we will cover it much better in a later lesson when we're dealing with properties of radicals. But basically, again, for what we need to know today, 16 square root is 4 and 25 square root is 5. So the actual number we're looking at is 4 over 5, which is rational. That is, it's a fraction, so we know it's going to be a rational number. And it is a real number because just about everything is a real number. All right, so now on to number 9, we have 0.15 repeat. So this number, if we were to write it out the long way, it would be 0.1515151515 forever. But we got better things to do, so we're not going to write it numbers forever. So we're going to put a little line over the top of it to show that it is repeating itself. So in this case here, well, what can we write it as? Can we write it as a fraction? Now this one's actually kind of a tricky one because in this case, it would be actually able to be written as a fraction. I just don't know the exact combination of numbers that I would have to write in order to get it. I think it's 1 divided by 9 actually. Or something like that. But well, in this case, I know it can be written as a fraction. I just don't have it right off the top of my head, but that one's actually a really tricky one. Number 10. Now this is well, it's definitely a whole number because we don't see any fractions or negatives. So it's definitely a natural number also because you can have 109 rocks. So this is natural. It is whole. Oops. It is an integer. It is rational. It is not irrational, but it is also a real number. Oops, let me get that R in there. Oh, Q, I forgot Q. So there you go. It's actually just about everything. It's pretty much all of the things we've already covered. So that's kind of what you got to do. You got to make sure you have all of them put in there too. So again, think of the most specific one that it would belong to, and then start from there. Like for instance, in this case, it is a fraction, so it is most likely a rational number. And then as we look at rational, we think what else is it? Well, it's not really anything else because it's not an integer, it's not natural, it's not a whole number. So it's probably only a rational number. Now this is another one of those number properties, but any number divided by itself is always going to be 1. Like if I have 5 divided by 5, that would be 1. If I had, 5,000 divided by 5,000, it would be 1. So it's just one of those number properties, again, one of those things that numbers always do. So in this case here, we have, it would definitely be a real number. And for these, I'm not having any real pattern on this, but 1 can be written as a fraction. And remember, we're looking at 1, not root 7 over root 7. It is also an integer. It is a whole number, and it is natural. 1 is natural, it's whole. So again, we got to look at our diagram here. Oopsie, let's see. So since it's on our inner circle here, the innermost circle is natural, whole, rational, and an integer. It's all of these things. So there we go. That's how you would do that assignment. We don't have that much further to go. So it looks like we only have about 3 more left. So moving on to the next set of exercises. For this one here, I'm going to go ahead and just put them in here. So here are the properties that we already have. So for commutative, we have A plus B equals B plus A. Okay, so if I asked you what is 7 plus 5, and would that be the same as 5 plus 7? Are they the same thing? Well, yeah, right? Because they're both 13. It doesn't matter which one goes first. It would be the same thing. And the same would be true if I were to go 7 times 5 and 5 times 7. So they both would be 35. And that's, again, commutative property. The commutative property states that the order of which you add or multiply numbers does not matter. All right, now associative. I don't really have a really good example for this one, but let me make something a little bit easier. So we all know a little bit about the order of operations. So if I were to have something like 2 plus 3 plus 4, would that be the same as, let's say, 2 plus the sum of 3 and 4? Put a little bit of space in here just so it makes a little bit more sense. Would these two things be the same? Well, we could try working them out. So 2 plus 3 would be 7. So I'd have 7 plus 4, which is 11. And over here, I'd have 3 plus 4. So 3 plus 4 would be 7. And remember the parentheses say that we should do those first. And here I have 2, so that's 2 plus 7, and that would be also 11. Now you might be thinking, well, how is that different than commutative? Well, commutative says the numbers you add or multiply doesn't really make a difference, but associative is a little bit different because with associative, the key word is the groups. The groups are what don't matter. So here I grouped 2 and 3, and on the other side I grouped 3 and 4, which actually these are the same numbers and they are the same order. 2, 3, 4, 2, 3, 4. Same numbers, same order, different groups. So again, the associative property means that the grouping does not matter. Also, you can remember this easily by thinking about the word association. So I'm pretty sure you've seen the word association plenty of times, although usually as a young person, you're not really in a lot of groups, but like, for instance, AARP, the Association of American Retired People, is a group. And as from its name, it means that when you're retired, you can go to that group. You know, there's also like the Homeowners Association. And there's all sorts of associations all over the place too, if you look, but association just means group. Or your friends, you might call them associates because they're part of your group. So anyway, let's move on to the next one. The next one is identity property. So for identity property, let me see, what if I were to go with 5 plus 0? Well, 5 plus 0 would be 5. Because if you add 0, that doesn't change anything. And if I were to go 5 times 1, that wouldn't be, it would stay 5, right? So basically, you did something, but it didn't make a difference. And to kind of help you remember the property, like if you ever watch superhero movies, which become very popular recently, usually something happens to a person and it forces them to become a superhero. Or they decide to become a superhero shortly after something happened to them, something big, something drastic. You know, well, I'm pretty sure I could ask some nerd buddies of mine, but there are very few, if any, superheroes that just like woke up one day and said, you know what, I'm pretty strong. I'm pretty, you know, I have a power. I should just go do some good stuff. You know, I got both my parents, I got like a family, but I'm gonna go ahead and do things anyway. That almost never happens. Come to think of it, that's kind of like Mr. Incredible, but we don't know Mr. Incredible's backstory. I don't know. It never really explained why or how he became Mr. Incredible, but I'm guessing he was born with it because it looks like most of the people in that movie series are born with their powers. That's actually kind of a boring story. Anyway, identity means you stay who you are even when something happens. So something small happens, like you eat a burrito. That's not going to change who you are. You're still going to be the same person afterwards. You've probably eaten many burritos in your life and you're still who you are. All right, next one. Let's move on to the next property, inverse property. So for the inverse property, it states that if you add a number to its opposite, so like in this case here, I guess while we're going with 5, let's just stick with 5. 5 plus -5, that would be 0. So for addition, you're trying to get to 0, but for multiplication, you're trying to get to 1. So let's go ahead and, for the multiplication one, I'm gonna go ahead and I'm gonna pick a number, let's say 8, I haven't picked 8. So actually I'm gonna pick an easy number. Let's stick with 5. So I know what this is, but I'm gonna show you where I got this number from because this next number is gonna be kind of a weird one. So we need the inverse of 5. So the inverse of 5 is 1 divided by 5. So 1 divided by 5 and that's going to be 0.2. 5 times 0.2. Well, what happens if we go to 5 times 0.2? Well, actually, you know what? I have the calculator ready here, so I'm going to go ahead and switch over to that calculator, clear the last problem off, and 5 times, oops, I need times, 5 times 0.2. We get 1. 1 is the inverse, 0.2 is the inverse of 5. Now, if we go with, let's say 1 divided by 10. So let's go ahead and use 10 now. So 0.1 times 10 is 1. And you're probably thinking, wait, didn't you just take that number, divide it, and then times it by the same number? Well, yeah, that's kind of what we did. But it's still the inverse. So let me go ahead and get back over to the main screen. With multiplication, you're multiplying it times what we call the reciprocal. So like I could write this problem as 5 times 1 over 5, and that would still give me 1. So that's the inverse property. So again, with addition, subtraction, you're trying to get to 0, and with multiplication, division, you're trying to get to 1. Now you can't really multiply to get 0 because that would be an entirely different property, what we call the zero product property, or multiplicative property of 0, sometimes as we call it. Distributive. So distributive is going to be, well, if you have a group, so you have, in this case, addition, but it can also be subtraction. You're multiplying a number on the outside times that group. So let me go ahead and make an example for this one. Let's say I'm going to change the color just so it's a little bit easier to stand out. So let's go with 2 times 5 plus 3. All right, so I can add these numbers. So 5 plus 3 would be 8. 8 times 2 is 16. All right, so I followed the order of operations. I did the parentheses first. But what if I were to do the multiplication first? So what if I were to do 10 and multiply, 2 times 5 is 10. 2 times 3 is 6, and we still get 16. So a lot of times, they kind of tell you to multiply it like this, and they'll draw little arrows to show that you multiplied both of the inside numbers times the outside number. But again, distributive, I think, is one of those things that, you know, if you're in Algebra 2 now, distributive is something that you would have covered for several years by now. So hopefully I don't need to explain it that much. But yeah, it's just, again, multiplying using the parentheses. Now, when you do this, sometimes you'll have a big group, but you got to make sure you multiply everything by the outside number. So distribute is like to give stuff away. Like, for instance, during this past year, we've been having food distributions at the fairgrounds. So that's where you would go to get food if you need additional food. That's distributing food. All right, moving on. Name that property. So let's look at what's going on here. 5 times, well, we would read this as 5 times the product of 2 and 8, because this parenthesis says we should do it first. Now, we're not trying to solve, or we're not trying to evaluate this answer. We're trying to get the property that it is, that it's showing. But let's look at the order: 5, 2, 8, 5, 2, 8. So you might be thinking this is commutative, but it's not. What's the thing that makes this one different? In this case, it's the group. The order did not change. The group changed. So instead of grouping 2 and 8, they group 5 and 2. So that would make this an associative property problem. All right, so let's go ahead and look at this one here. So we have a parenthesis. Does that mean that this one is associative as well? Now be careful, because sometimes they will be tricky, because this one does kind of look like associative, but it's not associative. In this case, what's going on? 3 is times by 7, I'm sorry, 6. But 7 is also times by 6. So this is actually a distributive problem. So both numbers were multiplied by 6. So again, if I drew little arrows on top of here, well, actually, let me go ahead and do that right now. You would see that they were both multiplied by 6. Let's move on to the next one, number 15. So we have 7y plus negative 7y. So when you have something like that, it goes back to 0. So this is what we would call the inverse property, because we did the backwards of it. Inverse means like backwards. Like if you were to turn your jacket inside out, you inverted your jacket. Basically, you made it backwards. Or like a car goes in reverse when it goes backwards. So it's gone, you had 7y, but you minus 7y, so it went backwards, an add and a subtract. Okay, so here we got some letters, but don't let that scare you, because here I have 3a plus 2b and 2b plus 3a. Now there's multiplication going on, but 2b and 2b are still together. 3a, still together. So we didn't change any multiplication, we only changed the addition. And in this case, we changed the order. Order means which one goes first. So since the order has changed, and that would make this one commutative. So again, order is which numbers go first and second or third or whatever. I don't mean the kind of order you get from McDonald's. Hey. All right, so let's look at this one here. So first off, let's look at the order. Whenever you have something like this, the order might change. Now, sometimes they can be multiple. Well, not for this assignment. I think it's only one thing for this assignment. But in common math and in regular math, you can change both order and grouping sometimes. So in this case here, we have the order is the same, x squared plus 8x plus 1, x squared plus 8x plus 1. So it's the same thing. So it's not commutative. So in this case here, the grouping is what changed. So in this case here, the first two were grouped, and here the last two were grouped. So the grouping changed from, here to there. So the grouping changed. And again, association is group. All right, let's move on to this one. In fact, actually, this is the exact example I used on the last slide. But this is what we would call the inverse property. And here, let's see, continuing on, this would be, let's see what's going on with this one here. Now this is actually factoring. If you're looking at it from left to right, it's what you would call factoring. But this is distributive because 3 times m would give you 3m, and 3 times n would give you 3n. And that only leaves us with one property left, and that, okay, so in this case, you probably already knew that. I'm just moving the letters over, and this would be identity. And identity is, again, means that nothing changed. It's the same as it was before. So 9c plus 0 equals 9c. Well, it was 9c to start with, and it stayed 9c, so nothing happened. So anyway, those are all of the properties that we have here, and that's pretty much it. I'm going to move on over to the next one, and I'm going to go there right now. So with this one here, name the additive and multiplicative inverse for each number. Whew. So for this one here, we're going to have to use our properties. So let's say that we have -8, and I want to get to 0. What do I have to do to -8 to make it into 0? Well, we would add 8, right? So we would add 8. So 8 plus 8 plus negative 8 would be 0. So there we go, we got that one. And this one's gonna be a bit of a tough one. I'm gonna see if I can write it. We have to shrink the writing a little bit. But now when you are using the multiplicative number, see if I can put that in there. It's supposed to be a fraction of negative 1 over 8. So it should look like that. Now you don't change the sign because in this case, negative times negative would give us positive, and 8 times 1/8 would give us 1. Okay. I hope I'm not confusing anybody. Now I'm gonna go ahead and just write these freehand because I think it's the best way to do this. So additive, so what do I need to add to 2/3 in order to get 0? So in this case, it would be negative 2/3. Because 2/3 minus 2/3 is gonna be 0. If I put them together, if I put this with that, it's gonna be 0. But what do I need to multiply in order to get it to be 1? Okay, so I mentioned the word reciprocal, but I probably didn't explain it all that well. So with a reciprocal, you take the fraction and you flip it so that the top number becomes the bottom number, and the bottom number will be the top number. So instead of 2 over 3, we flip it to 3 over 2. Make that 2, make it look a little bit more 2-like. So again, just flip the number, and it's now 3 over 2. So if I multiply it together, I get 6 over 6, and 6 divided by 6 equals 1. All right, 6W. So with this one here, I got 6W. Let's see, 6W. So if I want to, what do I need to add or even subtract from 6W to get 0? Well, I would just minus 6W. And for multiplicative, now in this case, it has a whole number. So what we can do is make it into a fraction by putting a 1 under it, or just imagine it. Okay, just imagine that it's 1 on the bottom, or you could draw it. Okay, you could draw it. I don't think it would make a difference. So some people, when they draw it, it makes a lot more sense, I guess. But whatever works for you, you know, you can imagine it, draw it. But either way, you got to put that 1 under it and flip it. So in this case here, it would be 1 over 6W. Okay. Now here we have root 10, and this one's going to be a bit of a tricky one. I can already imagine some students looking at this being like, how do I reverse the square? Well, maybe you don't have to. We could just subtract that exact same number and it would still give us 0. So don't let the square fool you. You might be thinking that you have to do something with the square, but no, you don't have to. Negative root 10 is perfectly fine. Because if I put root 10 and negative root 10 together, I get, well, negative root 10. And the multiplicative, how do I multiply it to get, okay, you probably can't see that all that well. Let me redo that. But it would be 1 over root 10. Let's, 1 over. Now I have to write mine really small just so it'll fit in there. I don't know if I can make that bigger or anything like that. All right. Now this last one here, it didn't really give us a whole lot of anything to work with before it gave us this problem here, but there's this example of closed. So in this case here, integers are closed under multiplication. If you multiply an integer times another integer, you will get an integer. Whew. Okay. Irrational numbers are closed under subtraction. So in this case, it would be false. So if I have an irrational number and it says use subtraction, so let's use an example. Darn, how do I type? Okay, I'm probably have to write it out because I can't type it out. But if I have pi, that's an irrational number. If I subtract another irrational number, I don't get an irrational number. I get 0, which is rational. So closed means if you have two of them, so again, if I have 5 times 5, 5 is an integer, 5 is also an integer, they're both integers, and the answer or the product is also an integer. But in this case here, closed, we can get out. So since it's not closed, so irrational minus irrational is rational. That means it is not closed, which means it is false. Whole numbers are closed under division. So if I have a whole number divided by a whole number, can I get something else? Can I get a non-whole number? So a whole number, so let's go with 2 divided by 3. So 2 is a whole number, 3 is a whole number, but as we've seen before, we get this repeating number here. That repeating number is not a whole number, so in this case, this is false. I can take 2 whole numbers, divide them, and I can get something that is not a whole number. So again, closed means it stays within its own group. So this is not closed. Odd numbers are closed under addition. So think about it. Adding 2 odd numbers. If I add 2 odd numbers, will I get an odd number as an answer? So an odd number I can think of is 3 plus another odd number I can think of is 5. 3 plus 5 is 8, which is not odd. So we went outside the group of odd numbers. So in this case here, this would be false. So again, that's what closed means. Closed means that you will get the same group of numbers. So here we're working with the group of integers, the group of irrationals, the group of whole, and the group of odd, which odd is a subset of integers. All right, and again, that's what, well, the definition's right there. That's probably the better way of saying it there. The operation produces an element in the same set. So again, integers multiply other integers is true. And here when it says give a counterexample, it's like, okay, well, if you say it's false, then why is it false? Think of an example of where it is false. So we gave these as examples. So I hope that kind of makes sense, but this is pretty much the only exercise that this appears in. So anyway, that is it for today. That's all of the examples that you would need for this one here. If you have any questions, you can go ahead and I'll let you stay by for a little bit. And if not, that is fine because we are done here. Thanks for showing up. All right, bye-bye.